All right. Good afternoon, class. We've been our project was supposed to be a can crusher. We assumed that we were a consulting firm that was commissioned by the state government to produce a can crusher, and so this was to to produce a product that was capable of crushing cans, and this was for recycling and recycling for future projects by the state government. And so this was supposed to be put on a busy metropolitan street in the city of Melbourne, and any pedestrian could insert a coin to be crushed, and a coin would be dispersed as a reward. So the crusher, as stated by the government, needed to crush to approximately 15 millimeters in height, and the chamber was to crush an individual can at a time. And they were supposed to be stored in a chamber as well. So additional information that was given to us in the project document was that the average can height would be 150 millimeters to 155 millimeters, and the typical diameter was 65 millimeters. And also the average mass of the can would be about 0.02 kilograms. And in addition, our client preferred to outsource its electrical components, and so this also indicated to us that electrical components were a part of the project scope. And our client also had a preference for low shipping costs, and so we had to pay careful attention to the dimensions of parcels and also the weight of the electronic components. So this is our needs analysis table. So from the information provided, it's now time to eliminate some ambiguity of the project, and so we decided to what could be implemented and what couldn't be implemented. So the first constraint was that we need to abide by safety regulations. We needed to, in this case, it was in a public space, so we needed to install a guard on the crusher. So we also needed to design the product in such a way that even if someone wanted to hurt themselves, they couldn't. So that was a part of the equipment regulations for public safety, 2017. That was, yeah, that's a regulation document. So because of the dimensions of the can, the chamber, the crushing chamber needed to be greater than the largest can size. That was 150 millimeters. And the cross-sectional area or diameter needed to be larger than 65 millimeters. And the axle needed to withstand a force greater than the amount of force needed to crush a can, and also the casing needed to withstand that force. A coin mechanism also needed to dispense a coin, and talked about that when a can was detected to be crushed. And they need to be stored into a container. And the assumption is that at some given period of time, the container will be emptied. And the last requirement, sorry, this is actually put on two different slides. So that's our table there, that's our table there. And the last requirement was that we needed to outsource our electrical components, and yeah, that was to reduce the cost. Once those needs were identified, we decided to create, we did a rank of importance. So as you can see these numbers here on the third column, that's the rank of importance. So from 10 being the least important to 1 being the most important. The most important was the guard that we had to put on. Yep, so it needs to abide by public safety regulations, as we said. The axle needed to withstand the amount of force needed to crush a can. That turned out to be 250 pounds, which came out to be 1100 newtons. And this is also true for the outer case. That was in the specifications there. And an ejecting mechanism also need to be put in as well. And we actually did this based on statistical data from the city of Melbourne. And so the busiest street, which was Bourke Street, had the highest amount of pedestrian traffic. And so based on this, 5,000 pedestrians passed every minute. We assumed that, because that was the busiest time, assuming that 25% were carrying a moving can, and assuming that 25% dispose of it. Doing all of those calculations, we decided that the storage container needed to be approximately 400 millimeters squared. and a lever or a button system needs to be implemented as well for them to operate the machine. And we weren't sure at this point whether or not a lever or a button needed to be used for the can crusher. And I'll pass it over to Tom because he'll be talking about
the meeting minutes
and the Gantt. And
yeah, all right. So this is our first meeting recorded. We did it in Discord. We just spoke about what we expected from each other and how we wanted to break down the project and tackle it. We split the work between us, and then we scheduled another meeting for the Wednesday after. And we ran meetings most Wednesdays after class. Safety of our design. Can you go to the safety slide, James? Cheers. So safety was paramount to our design. It was probably the most important thing. We had to make sure that people couldn't injure themselves. If someone's going to injure themselves, then it was just a waste of a product. We couldn't really implement something that was a hazard to the public. We even tried to make it so you couldn't intentionally or reasonably intentionally injure yourself by making the door. The door had to be closed before a can could be crushed. And the crusher had to be stable, so when it was in use, it wouldn't fall over or fall over in the wind or something. Next was the mind map. So yeah, we split this into the six most important parts. The seven most important parts, I mean. No, the six, what am I talking about? So the budget, efficiency, safety, functionality, size, and the materials it was made out of. This allowed us to then just easily break it down and split it between us, and made it very, very easy for us to communicate how we wanted to do that. The Gantt chart. Oh, yeah, there it is. I need to pull that up. This was probably one of the most important things. It made it really, really easy for us to see what we had done, who was doing what, and then when we put this final PowerPoint together, it allowed us, we knew who had what, so we could just easily communicate between each other and get the correct work. This also allowed us to rank the priority of the work that we had. So the design concepts are obviously much more important than the scope. And what else did we have? The work breakdown structure. So we split it into 5 different parts: the needs, the specifications, execution, control, and shutdown. So this allowed us to successfully divide up the tasks, and it also helped with ranking importance of each trial design. All right, I'll hand over to Flynn.
Okay, so with the QFD, James and I both had original ideas that we had each thought of. In a group project, it's best to have multiple designs, and so James and I were able to each think of a design to base off with. We then touched base again in the next meeting and tweaked both of our designs to better suit the constraints that the project had provided us. After that, we were able to compare the two designs, and they cut very thin on what we had then chosen to go with for the final design. As we can see, the scores ended up totaling to 7 and 7.5, so it cut very thin, and obviously it wasn't going to be a 10. There was going to be some things that we had to improve on from there, so the design did actually change slightly after having done our QFD, and that'll take me into the next thing, the bill of materials. So throughout the bill of materials, there are a lot of things that we had to consider that we had talked about later on to the semester, which was with our sustainability, the quality of the product, and the life cycle of the product. So considering all of these things, we've done a little bit of research and opted to mainly use cast iron because it is highly recyclable and has, in some cases, actually been proven to be the least damaging to the environment during the production phase. And I believe that was largely because of how recyclable it is, and that a lot of the products that are being used have been used somewhere else before. The other products that we used were ferric stainless steel and polylactide, which is what you could see in electrical components, and sort of our mechanisms was largely the stainless steel. Our chamber and whatnot was obviously the cast iron, making it more durable and capable of withstanding the force that was going to be exerted on it from crushing a can. So the next thing is the designs. If you want to, yeah.
Yeah. So just going back to the designs that we were coming up with. So the first one we did, this was a bunch of gears. It's a bit hard to see, but I'll explain it. So yeah, so it was literally just this one was operated by a lever, so it had a system of gears. So the gears, one of the gear operated another gear, which, as you can see, it's a rotating axle. And so when initially it's receded, and so is the other one. So and it was supposed to be that when you pulled down the lever, the crushing axle will. Sorry, can you hear me? The crushing axle will come down, and you'll crush the can, and then when it came back up, the ejecting axle, sorry, it was connected to the gear which the lever was connected to, and so that would actually push the crushed can as the lever came back up, it would push it into the container. So and also had a hole, so it was like a cylindrical hole where you would put the can in, and so that would act as sort of like a safety mechanism, so no one could really like reach down and crush their can or crush their hand or anything like that. The next design that we did, hang on. Yeah, the next design that we did, instead of, it was the same one as the first one, but instead it was operated by a couple of motors. So it still had the crushing axle. It had, as you can see, there's two motors in the middle of that. And also the ejecting mechanism down there is also operated by two motors. So, hang on. Yeah, so so it operated in the same way. So you just had those two things going on, and there was this off and off button, and it still had the hole there. And then I'll pass it to Flynn and for his design that he made.
So with design 3, it was the same thing. It was a manual concept where you would pull down the lever. As you can see by the bottom half of the screen, there is a sensor and there is a receiving end. Once the lever would be pulled down, the sensor would hit the receiving end, and that is what would trigger a coin to be dispersed. The only problem and flaw with that is that you never can guarantee that a can is actually being put into the system and being crushed. Someone could sit there and pull down on a lever all day, and it would be dispersing coins without a guarantee that they're actually helping the environment in any way. And that is what took us to our design 4. The design 4 was mostly electrical operated, and this meant that the system was working independently as opposed to being correlated to the whole design itself. For example, in the design 3, it meant that one system, the button, was operating the crushing mechanism that would crush the can. We then had a slip in the back of the chamber, so that once the can was crushed down to a certain height, it would slide down, considering that the base of our chamber was on a slope, and that would fall through, running past a flow sensor that would trigger our coin dispensing to actually activate. So that it was two independent electrical operating mechanisms, and that was what made our design foolproof in a sense, so that we could actually guarantee that someone was actually putting a can in the crusher every time. Also, we had added the door. If you could go to the next slide, please, James. Yeah, we actually added a door. It's hard to see from this one because we wanted to show the inline casing of the chamber and how it was functioning, but there was actually a door on the front of our chamber, which meant it would have to be closed before the buttons would actually become operational. And that meant that no one could stick their hand in and operate the machine. The machine would only turn on once the door was closed. So that would take us to the next thing. James?
That's it. Yeah, thanks for watching. Thanks for listening to our product.
All right.
Thank you.
Thanks very much, Group 1. That was a nice presentation. Please give a round of applause for the group. Question from audience. We have maybe 1 or 2-3 minutes for asking questions. Question from the audience. All right. So if there is question, please be quick. Otherwise, I think I'm gonna keep the comments toward the end. I want to invite the next group to be presenting. Okay, we have a question from Cloud. Let us hear the question. And would you take the question, please? James, Tom, or Flynn?
I think realistically, if there is a power outage anywhere in the world, the last thing that someone would want to do is go to a can crusher and crush a can. I think the first thing that they would look for is shelter and safety. So I don't think that was really one of our main constraints.
Yeah, all right, good. Any other question?
Yeah, it didn't have a battery or anything like that. It was connected to the mains.
Any other question? All right, if there is no questions,